Hey guys, welcome. Hope you're doing okay. Hope this video gets up in time. I told you guys I'd get this up on Saturday, and yeah, I think technically that's going to happen, but I hope that you got plenty of time on Sunday to get this watched. I will post as soon as, before I leave the classroom, I will post the Chapter 16 Part 2 notes. I want to say one thing here real quick. This first problem, it's actually just a recap off of the Chapter 16 Part 1 notes. So why don't we save this problem for in class? If you guys would like to talk more about random variables, we can use this as a reference point. So what I'd like to do is jump to the second slide here. And the goal of the lesson is to continue the discussion of random variables in such a way that we're going to build shortcuts. We're going to come up with, I don't have this in front of me right now, but I think that next up is, we've already done that. We have covered, I believe, the next two equations in the AP Stats reference sheet below the probability general addition and conditional probability rules. We've covered that in the Chapter 16 Part 1 video. Let's go ahead and see where this new stuff takes us. So suppose that a casino table allows you to win $10, $20, or $30 with corresponding probabilities of 0.30, 0.50, or 0.20. A probability model of your winnings with random variable x, the mean of your winnings, and the variance of your winnings are below. Suppose now that the casino table feels like the winnings it's giving players is too much and shifts all of the winnings you can earn down by $5 without changing the probabilities of success for those three outcomes. What happens to the expected value, which is the mean, and variance of the winnings you can earn? Well, if you would, pause right here in the video, after you listen to this question that I'd like you to think through. Before I show you what happens, come up with for yourself a guess as to how the mean and how the variance, which is, remember, just the standard deviation squared, write this, that the variance of x equal the standard deviation of x. You got to take the square root, or you could also think of it, this is the square root of sigma squared equals sigma, to use symbols that we had early first semester. Okay, well, come up with a guess for yourself. All right, so I'm going to design another probability model here real quick. Or actually, no, I won't. I'll save time. Instead of 10, 20, and 30, the winnings have been shifted to 5, 15, and 25, so the expected value of x, remembering that that is the sum of, in this case, three different products. For each x sub I, for each individual data value, you multiply that by the probability that your random variable could equal that data value. So we're talking about an expected value calculated by taking 5 times 0.30 plus 15 times 0.50 plus 25 times 0.20, and when you simplify that out, you find that your expected value is just 14. Okay, so by shifting all the values down 5, perhaps unsurprisingly, the mean is 5 less as well. All right, so now on to the variance of this random variable. That's equal to the sum of products similar to the expected value. You've got x sub I minus the mean expressed as mu squared times the probability that the random variable x take on that individual data value. So this is the products, let's see, 5 minus 14, which we just calculated to be the mean, squared times 0.30, which I'm just reading from the equation above I used to find the mean, plus 15 minus 14 squared times that probability was 0.50, plus finally we had 25 minus 14 squared times the probability, which was 0.20. Okay, so the variance is, I calculated the standard deviation, which was 7, so the variance would be 49. So sure enough, we had a variance for the payouts at this table. When they were $10, $20, and $30, it was 49. Shifting the values by the same amount does not change the variance. Well, that should make intuitive sense if you're recalling that variance and standard deviation both are just measures of how spread apart the data is from the center. Okay? All right, so that takes us to the following two big ideas. The first, based upon the example that you saw, is that the expected value of a random variable plus or minus, add or subtract some constant from that, like we did here, we subtracted 5. That just gives you the expected value of the original variable plus or minus that constant. That is to say, instead of going through all this work to calculate a new expected value, we could have just said, oh, well, the expected value of the old variable was 19. I'm subtracting 5 here from all of my data values, so the new mean would just have to be 19 minus 5, or 14. Okay, so that's the first big idea. Second is that the variance of a random variable, too many of those slashes, the variance of a random variable x, if you add or subtract from that, it's unchanged. It is just the variance of x. And knowing that the standard deviation is just the square root of the variance, so that must mean, sort of as a sub-bullet, this is not so important. The standard deviation of x plus or minus a constant must therefore be just the standard deviation of the original variable. Okay? The data did not change in terms of how far spread out it was when you subtracted off the 5. Okay, so there are the first two big ideas. Now let's go to the next two big ideas. So, a term I want to throw at you. What we just did here, remember first semester we talked about how mean and standard deviation would change based upon shifts and scales. Well, shifts, as a recall, is adding or subtracting a constant to all your data values. So we shifted everything down 5. What we're going to do next slide, as you can read through, the casino manager feels like subtracting 5 for the outcomes, the win outcomes, was too much, and he's got too few people playing. So he takes the original values of 10, 20, and 30 and scales them or multiplies them by 3 here. So we want to calculate the expected value and the variance of the winnings you can earn. So if x is again defined to be amount won in a game, and notice that the random variables here, painting gambling as being really favorable. There are no losses in any of these examples, but that's just for the sake of convenience. Makes it easier to work with, to explain. So the x sub i's, the individual data values here, are 30, 60, and 90, because we said we tripled the original 10, 20, and 30 that we had for the payouts. So the probability that the capital X is equal to one of those data values, that hasn't changed. That's 30%, 50%, and 20%. Okay, so once again here, if we know we've multiplied the original probability table or probability model, excuse me, by 3, take a guess as to what the expected value and the variance are going to do for yourself. And I would start with, think about whether or not you think the mean, which is the expected value, think about whether or not that will change, and if so, by how much. Same thing with the variance here. Do you think the variance will change? And if so, how much do you think it'll change by? All right, I wonder if you guys can see what's going on right now. I've got a totally black screen. Okay, and I think we're back. Okay, so expected value, the mean of this random variable, looks like the following. We've got 30 times 0.30 plus 60 times 0.50 plus 90 times 0.20. I found a mean of 57, which is triple the original mean when you had payouts of 10, 20, and 30. The variance of this random variable is equal to sum. Oh, I don't want to write out the sum here. I'm not going to write the variance and expected value formulas because I've already done that once in these notes. So this is 30 minus 57, which we just calculated, squared, times your 0.30, the probability that you'd have a payout of $30, plus 60 minus 57 squared times 0.50 plus, finally, we had, let's see if we can fit this in, 90 minus 57 squared times 0.20. So I see a variance of 27, where, oh, excuse me, no I don't. That would be the standard deviation. Variance here is 81, which is okay. That's not right. Let me get the calculator here real quick. 27 squared is 729, which is actually 9 times the original variance that we had of 49. Let's see. 9. Where's the mistake? That doesn't make sense. 9 times 49 gives us 441. Plug this into my calculator here. I'm going to pause the video. Okay, so we're back, and you'll notice that I changed this to 441. I'm not sure how I miscalculated the standard deviation, which would be the square root of the variance here. But regardless, if you do a plug and chug on this long calculation for variance, you get 441, which that is 9 times the original variance for this original probability model of 49. Okay, so this takes us to the next two big ideas here, which are the following. We have, let's see. I'll do it. Oh, okay, forgot to write them in my notes. Sheesh. That if you've got the expected value of a random variable scale, this is multiplied by A. That just takes you to A times the expected value of the original random variable. That is to say, in terms of the meaning here, we multiplied the original probability model by 3, and thus we multiplied x by 3. And we took a long way to find the new mean. Well, this tells us right here that the new mean must just be 3 times the old mean. The old mean was 19. New mean we found to be 57, so we could have just taken this shortcut from the get-go if we had known about it. Okay, so the fourth big idea is that, kind of going from memory here because I didn't write this out, the variance of A times x, again, we scale the random variable x, takes us to A squared times the variance of the original random variable. So here too, again, in terms of the meaning, you multiply a random variable by a constant, which we did by 3 in this case. The shortcut tells us the new variance is just going to be, in this case, 9, 3 squared, times the old variance. 9 times the 49 gave us 441 here for the new variance. Okay, and those big ideas are going to round out a lot of the new stuff for Chapter 16, Part 2. We got one final slide of new. This one will take a little bit of time to get through. Suppose that you and Mr. Shelton can both try your luck at the casino table with winnings and probabilities for those winnings listed below. What are the expected value and the variance of your combined winnings? Okay. So let's say that I'm going to change this to be lowercase a. I'll change this to be capital A, and this will be lowercase a as well, because I want to use x and y because that lines up with my notes. I'm going to say that x is equal to winnings for Shelton, okay, and that capital Y is equal to winnings for you, okay. So if we want the combined winnings here, well, what this probability model does not do, if we want combined winnings, it does not tell us how many branching paths there are for these two random occurrences. We've got the paths for a single random occurrence if you or I played, but we don't have the paths for both, okay? Now, before I get going here, let's talk about real quick whether or not we think this is fair. Is it fair to assume independence? Well, it should be. I mean, unless we are playing at the same table, which doesn't say that we are. Let's assume that we're playing at different tables. Casinos tend to have many, many tables. Hoosier Park alone has I don't know, 50 maybe, combined among all the different types of games. There are a lot of different places you could play. So let's assume that we're playing at different tables, so therefore our winnings are independent random occurrences. All right. So what we're going to do is develop a probability tree, and I can win 10, 20, or $30 for playing with probabilities of 30, 50, or 20%. Okay, and then you would play and win 10, 20, or $30, and 30%, which we took to get for the first branch right here, times 30% for you being likely to win $10 as well, takes us to a combined probability of 9% chance that we both win $10. Okay, so the next leaf of this tree would be 30% times 50% from the model above, which takes you to 0.15, and we've got 30% times 20%, which is 0.06. Notice 0.09, 0.15, and 0.06 total to 0.30, which is what we're looking for. Okay, and we've got 3 more limbs with 3 more leaves of 10, 20, and 30 payouts for you, where we've got 50% times the likelihood you win 10, which is 30%, which is 0.15, 50% times 50%, which is 0.25, 50% times you winning 30 is 20%, 0.10, that totals to 50%, which is good. That's what we're looking for. And 3 more limbs of, again, 10, 20, and 30 payouts for you of 20% times 30%, so you get $10, 0.06, 20% times 50%, which is 10% total, and 20% times 50%, which is another, wait a second. Oh, that's 20%, not 50. 20% here, which is 0.04. Okay, 0.06, 0.10, 0.04, total of 20% in all. Okay, so we're good. All right, so that is a big tree, and the probability model from that, the different payouts that you could have, well, all I did to build the following tree that you're going to see, or model that you're going to see, is look at the payouts that are possible. Well, if I win 10, you win 10, that's a $20 payout. I'm looking through all these different branches to see unique combinations of win amounts. Well, one way I could have done this to save myself a lot of time, didn't take too long to do it another way, but I mean, at the bare minimum, you've got a $20 payout. At the highest, you've got a $60 payout, and it's staggered by $10 in between. So we're going to go from 20 to $60 in our probability model. Okay, so I'm going to call this X plus Y. And in the second row, I've got the probability that the variable X plus the variable Y take on lowercase value of X, lowercase value of Y. Again, difference here, random variable is a description of all the ways the random occurrence can take place, in some sense, okay? Whereas Y, in this particular instance, that's just a single value that the variable can take on. Okay? All right, so my model looks like the following. So it goes from 20 to 60, so we've got 20, 30, 40, 50, 60, with probabilities, I'm just finding wherever I've got totals of $20, 30 or 40 or 50, for 60, 9% for the first, 30%, 37%, 20%, and 4%. Okay, so that's the hard work. Now let's go ahead and do what we've been doing here for a little while and see, well, if I take the expected value of what I win plus what you win using this new probability model, what do we get? Well, that's $20 times a 9% probability, $30 times a 30% probability, $40 times a 37% probability, $50 times a 20% probability, and 60 times 4% probability, or an expected value in all of $39. Okay, to get this, I did round a little bit with the original, let's see, right, I believe that I rounded this original expected value and variance just a hair. So this, notice, let's see, oh, no, that was it. Notice that this expected value of 39 right here, that's essentially, it's really close to being double the winnings that you or I would have individually. Okay, that should make some intuitive sense. Now let's look at the variance, the spread between your winnings plus my winnings. Well, that's for each of these values. 20 minus the mean we just found, 39 squared, times 0.09, plus 30 minus 39 squared, times 0.30, plus 40 minus 39 squared, times 0.37, plus 50 minus 39 squared, times 0.20, plus, finally, 60 minus 39 squared, times 0.04. So the variance comes out to be $99 in all, which, again, is pretty close to double the variance that we started with. So, final big ideas here. Fifth big idea is that the expected value of a random variable plus a second random variable is equal to the expected value of the first plus the expected value of the second. So the big shortcut would have been to say, well, if we know that both of these, if your winnings and my winnings both have means of $19, we would expect that the mean of the combined winnings would be about $38, okay? And then last big idea with the variance is that the variance of your first random variable plus your second combined should just be the variance of the first plus the variance of the second. Whoop, that's capitalized. Variance of the second. But we need to, with this condition right here, it's the only one of the 6 that requires this. You need independence for this to work. I started the problem by asking if it was fair to us to assume that our winnings would be independent if we would be sitting at different tables. And that's how we proceeded to demonstrate that the variance of these combined variables should be the combinations of the individual variances, the 6th idea. All right, this is tough stuff. And to give you sort of a preface as to what's coming up, you're not going to be working much with everything that I've done in red here. That's really rare. There was a lot of stuff that went into this. You're not going to be doing that. Last slide, same thing here. You might be doing some of the red occasionally, but it's mainly working with these blue ideas, hence the color coding being a little different. Same thing here, working with these blue ideas to understand the problems you're going to be given. In fact, a lot of these problems, if you can just see how to look at them the right way, they become very quick. And so in that sense, they're satisfying. You're not going to be doing lengthy descriptions. It's just a matter of figuring out how to view the puzzle, and then it'll unlock itself once you've got the right lens through which to view the problem. All right, last thing we want to look at here. Let me check the time. Let's not. Let's finish this in class.